Hello. Today we're going to look at lines, which sounds pretty straightforward, but of course we're talking about lines in 3D space, which makes our lives a little bit harder, I guess. Okay, so we'll get towards our definition. Okay, so to define a line, we basically need two things. We need some kind of point that's on the line, and we need the direction that the line is going in. Okay, if we have those two things, I think we uniquely have the line. And of course, this isn't a new concept to us. If we think about y equals mx plus b, the m is the slope. We can think about that as the direction. Okay, how steep or shallow it is, it's negative or positive. And then b determines a place on the line. And of course, we don't have to use that one, but that's a very straightforward one. That's the intercept. When the x is 0, the y is equal to b. So that's all we need for a line. But we're going to think about defining that in a slightly different way using vectors. Okay, so we're going to take P be our point in space, so our point in space that's on the line, and the arrow above it is simply the vector from the origin to P. So that's nothing hard there. And then D is going to be another vector. Okay, and that's going to give us a direction. So the line that's parallel to D, in other words, going in the direction of D, but through the point P, is going to have this equation. So we call it L of t, because we'll have that parameter t in just a second. So it's P plus t times by d. Okay, t is how far we're going along it. That's just some kind of scalar. So there's our equation again. So L of t is P plus td. And I'd say to kind of bring this back to the y equals mx plus b a little bit. Right, so the starting point in a y equals mx plus b is our b, whereas in our vector it's the point P. The direction is on the left-hand side, it's that M that tells the direction. On the right-hand side, it's that vector D. And then the how far to go in that direction, right? So as we're moving along a y equals mx plus b, the x tells us how far to move along it. And that's the role that the t plays here, right? That's some kind of scalar that tells us how far along to go. So that's the kind of the link between these two different versions of looking at a line. So of course the one on the left is just in 2 dimensions as well. The one on the right can be 2 or 3 dimensions, or I suppose even more. Okay, so first off the vector equation, right? So if our point P is given by x0, y0, z0, then our direction D is given by ABC, then this is it, right? X0, y0, z0 plus t times by ABC. Okay, so we can take t to be any real number, and that will give us all the points on our line. We can simplify this a little bit, so let's put it all together. So we're putting the AT inside the brackets there, so we get x0 plus AT, y0 plus BT, and z0 plus CT. Right, that's the vector equation of our line. Okay, but we can actually move on to form this line in a different way. So just going back for a second, right? So the x here is x0 plus AT, the y is y0 plus BT, the z is z0 plus CT. So let's actually write those down, right? X equals x0 plus AT, and so on and so on. And in each of those equations, we can actually solve for the t. So rather than having x equals, we can have t equals. So t equals x minus x0 over a, y equals y, so t equals y minus y0 over b, and t equals z minus z0 over c. But you'll also notice now we've got 3 different things all equal to t. And of course, the 3 different things are all equal to t, well, they're all equal to each other as well. Right, those things are all equal to t, which means they're all equal to the same thing. And so this is the symmetric equation for a line. Okay, it looks a little bit different, right? It might not be intuitive that that's a line, but that is what's called a symmetric equation for a line, in R3 in this case. There we go. So just putting them all together, so we have the vector equation. So LT is P plus TD, the parametric equations, right? So they're in terms of the parameter T. And then the symmetric equation is the one where they're all equal to each other. And they're all just different ways of writing equations for the same line in space. Okay, so having said all of that, it's probably a good time to move on to an example. So here we have a point and a direction. So we want the line through the point 2, 3, 1 in the direction negative 1, 1, 2. Okay, the vector equation I think is very simple. we'll just take the 2, 3, 1 plus t times by negative 1, 1, 2. And that's about it. There's nothing much else to say about that. We can write that in a different form, just combining it all into one vector. So we get the 2 minus t, 3 plus t, and 1 plus 2t. Right, it all combines together, but there's no difference there. So that would be the vector equation. Parametric equation, well, again, it's very similar. We just sort of break it apart into our three pieces. Our x is 2 minus t, our y is 3 plus t, and our z is 1 plus 2t. So that's the parametric equation. And again, pretty straightforward. And I think you can see how you could go straight to the parametric equation from the point in the direction. You wouldn't have to go via the vector equation if you didn't want to. And then so finally the symmetric equation. So let's just take each of those x, y, and z and solve for t. And again, you can see it directly. You don't have to go via the parametric equations if you don't want to. So it's x minus 2 over negative 1, y minus 3 over 1, and then z minus 1 over 2. But again, because each of those things are equal to t, we can just set them equal to each other. So these are all equations to give us this one single line that goes through 2, 3, 1 in the direction of negative 1, 1, 2. Okay, here's a question we can ask, and there's more than one way to answer this. Is that point on that line? Okay, we have this line moving through space, and well, is that point on it or no? As I said, there's more than one way to do it, but I think what we'll use is the symmetric equations. Okay, so recall that the symmetric equation for that line was given here. And if we have this, all we have to do is plug the points or the elements of the point Q into these symmetric equations and see if it works, right? Are those three things really equal to each other? So we plug in negative 166. And what do we get? Well, in the first case, we get 3. In the second case, we get 3. In the third case, we get 2.5. The only way that point could be on that line is if all three of those were equal, which they are not. So that point is not on that line, is our conclusion. Let's just have a little look at the graphically of what this looks like. So on our axes here, you can see we have the point P and the direction D, right? The direction D there is starting in the origin. And you can see the actual line we formed, the blue line goes through P, but it's parallel to D. Okay, and so that's the equation of it. And, well, as you can see from how we've drawn it, it turns out that Q is not on that line. Right? Q is off that line, which is what we showed. Okay, so a point direction gives us a line, and then we have the other point Q, which isn't on that line. Okay, so here's an interesting question. So suppose we have two lines in 3D space. How can they be related? Right? You might want to take a couple of pens, right? Pick up a couple of pens and see what you can do, how you can relate those two lines with each other. Okay, so the first option is, well, they're simply what we call skew. Right? They're just two random lines in space. They don't intersect. They're not parallel. They don't ever really interact with each other. They're just kind of hanging out there. And so we call that skew. Another possibility is that they do intersect, right? So they're not parallel. So if you imagine if you have your two pens putting one on top of the other, they would have some kind of point of intersection, but just one. But that would be it. Another possibility is that they're literally just the same line, right? They're on top of each other, so they're literally just the same line. All their points are the same. And then the final possibility is that they're parallel. So in this case, they wouldn't intersect, but they do have the same direction. Right, so they're heading in the same direction, they're parallel to each other, but they don't intersect. Okay, and so let's take two lines and compare them. And here we've got a couple of lines with slightly yucky decimal values here, and that's really so we can't just kind of guess. I don't think we can just look at this and say, oh yeah, they're obviously parallel, or obviously the same line, or whatever it might be. We do have to do something with them. So let's determine the relationship between those two lines, L1 and L2. Okay, so first off, let's just take their directions, right? So obviously their directions are just the 1.6, 2.72, and negative 3.36 for L1, and similarly for the L2. But even here, I don't think this tells us, well, are they going in the same direction? Now, there's a couple of ways to think about this. One is we could just scale them to make the first entry equal to 1. But I think, one other way to do it is make them so they both have magnitude 1. So if you remember back when we talked about vectors, we talked about a unit vector that's in the same direction, Okay, so unit vector in the same direction as D1 is just divided by the magnitude of D1, and we get 0.3471, 5901, and negative 7289. And if we do that for D2, something interesting happens. We get the same numbers. Now, admittedly, the second one is a negative of each of them, but that just means they're sort of pointing different directions. But these two lines are, in fact, parallel. These are parallel lines. Okay, so they're pointing in different directions, but they are parallel. But we have to go a bit further than that, right? Just because they're parallel, are they the same line? Or are they parallel but apart? Right? If they're the same line, all their points would be the same. All the points would be on both lines. If they're parallel but not the same line, well, actually none of their points would be in common. And so let's go ahead and think about a point that we can find on either of these lines. And the simplest way, I think, let's just take this first line. If we set t equal to 0, we get a point on that line, which is the negative 0.7, 4.2, and 2.3, right? That's a point on that line. And let's take that point and plug it in to the symmetric equation of L2. Right, so the symmetric equation of L2, we'd have x minus 2.8 divided by negative 2.9, the same, and the same. So let's go ahead and plug this point into here. Okay, so we've got the negative 0.7 here, the 4.2 here, and the 2.3 here. Plug all those numbers in, crunch the numbers, it's not all that hard. Just simplify it down a little bit there, and sure enough, in fact, they are the same. We get 1.2069 for all three of them. So what does that tell us? It tells us that L1 and L2 share a point. But we've also already seen that they're pointing in the same direction. I mean, one is negative and one is positive, but they're both parallel to each other. So if they've got a point together and they're pointing in the same direction, they're parallel, in fact, what happens is they have all their points together and they're the same line, albeit facing in different directions. So in fact, it turns out, even though it's not obvious to see from their initial equations, in fact, they are the same line. Okay, so obviously this was chosen in such a way to create that. In general, if you just pick two lines at random, they'll be skew, just because, you know, think about space is very big, so forming two lines to be the same is hard. But yes, in this case, they are the same line. Okay, and that's all we have for today on lines.